I'm a programmer from Team 8227, Area 52, and today I'm going to tell you guys how to use Kalman filters for fusing sensor data.
Let me get rid of this for you a little bit. Go ahead.
So this is just for an overview of today's presentation. So I'm just going to talk about our experiences and lessons from last year, and I'm going to show you why I decided to research Kalman filter, and then I'm going to explain the Kalman filter. And then after that, I'm going to show how to implement it to use it for localization, and I'll show you pictures and compare it to other localization methods. So here's just an overview of past season. So last year we were lucky enough to go to the World Championship, and we had a pretty good performance at the World Championship. We had a win-loss ratio of 8-2. We went to Elands, and we had team second. So for our climbers, we ran Roadrunner 1.0 with AbleTag backdrop relocalization. But we had some inconsistencies throughout the qualifications. So that's why I want to talk about what I want to learn from last season's World Championship. So the first issue, the most embarrassing one, was the two odometry disconnects. So and then the second one, you can see over here, we got 150 penalties, more penalties than points. So yeah, so we broke pretty much 3 robots in the entire qualification, and it was kind of funny, but not because we lost. So yeah, but more importantly, I want to focus on the inconsistent stack alignment and the tag leading delay during that the times. So that's why. That's why I want to use the Kalman filter, which helps interpolate able tags and odometry readings, and so that I can use able tags during motion. So the Kalman filter has 3 main parts. First, the measurement. Second, the state or estimate, and then third, the Kalman gain. So for the measurement is basically what you read from a sensor. So that could be either from your AbleTag localizer, maybe a distance sensor, or odometry. So the measurement also has a variance, which also is basically how uncertain you're about the value. So using this example, you can see how a high variance has a bigger range of values and likely to deviate from the true value. And then we also have the state, which is basically the output of the Kalman filter, and also has a variance too. And then the last part is the Kalman gain. So using this equation, you can calculate the Kalman gain, and this is used as a trust weight on either your estimate or your measurement. So let's say we have a high Kalman gain. That means we have really high state variance, and we should trust the measurement value. And for low value, we should trust the state of value, because the measurement variance is very high. So here's just a schematic of how the Kalman filter works. So in the red box, you can see you're supposed to initialize your values first. So that's going to be your value and your variance. So for input value, you're just going to put your start pose for the localization example. So that could be in the origin. And then for your variance, I just put 10 as just the baseline. So, and then in the green box, it's going to be after every time you loop through the for the localizer, every time at the beginning of the loop, you're going to have to input your sensor data. So that can be for my example, it's going to be the AbleTag and the odometry. And with each sensor data, you're also going to put the uncertainty or the variance. For a DOM tree, because it's gonna have like constant drift amount throughout, I just put 10 as a constant. And I'll talk about this later, but for the April tag, I put a baseline of 2, and then I add velocity because while you're moving, it can be inaccurate. And then after that, you're going to update the common gain by using the measurement data, measurement variance and the state variance. And then you're gonna calculate the state and variance, and then you're gonna predict because the common filter is only used for like stationary values, but for this case, because the robot's moving around, we have to adjust for that. So here are the 2 equations that we're going to use for the common filter. So for the first one, that's going to be the value update that you're going to have to update. In this example, you're going to update your pose. So as you can see in this equation, we're going to be using the common gain, which is denoted as K, the measurement, which is denoted as Z, and we're going to use the value from the last loop, which is done as xn and s minus 1. So basically, this updates your localization. And then for your estimate update, for your variance update, you're just going to be using the common gain and the variance from last loop. As you can see, I ran 2 common filters, 1 for each, the x part of the pose and then the y value of the pose. This is so that I can because usually common filter is only used for 1 variable, so I just decided to use it for both variables. And then the second step, especially if the values are changing constantly, you're gonna have to use a prediction step. So for the prediction step, I used Roadrunner velocity, which is from the odometry sensor. And I use that to basically predict the next pose and then the next variance. Because when you're moving, data becomes uncertain. So you're gonna use velocity times time, like similar to how physics works, velocity times time is position. And then for the variance, I just did velocity times time squared. So yeah. Some things to note when you're using Roadrunner to predict your next position is you always rotate your velocity to be field centric. So whenever you're using the pose velocity from the Roadrunner, it's gonna get the velocity from the robot. So let's say you move forward straight, but it's at an angle. It'll only show that it's going straight. So you have to use the heading of the robot, which is where it's facing left to right, and you're gonna rotate it using this function over here. So after that, your velocity is going to be field centric. So that way your prediction is going to be correct. And also an important thing I want to also note is when you're adding your velocity to the variance, make sure to always take the absolute value of your velocity, because sometimes if your velocity is negative, it's going to cause the variance to become negative, which also makes the common gain negative, and it causes really weird spikes. And yeah, so always make sure to take the absolute value. All right, so by using this code over here and this code over here, we can finally finish the common filter. So by combining all that, you finish your common filter. And like I said before, for the variance of the April tag, I also added together the velocity of the robot, because especially when you're using April tags to localize. When you're moving, the camera has a lot of motion blur, and that causes a lot of the localization, like what the values it gets from the April tags to be very inaccurate. So I just added extra variance for the April tags to trust it less whenever it's in motion. So yeah. So here's some results I got. So for the drift test, I put like 3 sides of tape in the middle of the field, and I basically coded a position lock basically to move the robot to the center after driving it for a bit. And the goal of this test is to see if the robot matches the dashboard. So in the red, you can see the output of the Kalman filter, and the robot matches pretty close. It's just over the tape a bit. That's why you can't see the tape. Yeah. And also for just to see the Kalman filter working, you can see how the Kalman filter is really smooth, but the April tag is really noisy, and that just shows to how Kalman filter basically smooths out noisy data. And as you can see in the dip here, you can see it converging to the tag. So it's useful, especially when you have noisy data like distance sensor also. So why do you want to use Kalman filter? So let's say we don't use any Kalman filter. Let's just use 3-wheel or 2-wheel odometry. The problem with odometry is sometimes the wheel can slip, right? Which can cause a lot of drift. So in this example over here, you can see in the drift test, it drifted a lot from the tape after driving it for a while, especially in 3-wheel odometry, when drift can mean heading drift, which means that your localization, it will tilt your heading to what it's not, which will basically mess up your entire localization. And some teams, they completely rely on April tag relocalization. Well, this might be fine, but especially when you're using like a cheap camera like C270s, the Logitech C270s, the regular ones everyone uses, has a lot of motion blur, which causes the data to be inaccurate. So that's why we want to use Kalman filter, because last season we used just the relocalization, but since you have to stop like for 1 or 2 seconds before the localizing is consistently accurate, that means we only could use 1 relocalization per autonomous, which sacrificed a lot of accuracy. And also some teams also use global shutter cameras, which basically eliminates motion blur. But I feel like the C270s are cheaper because they're like $8, really easy to get. But global shutters can range up to like $100. So yeah, it's just some way to reduce cost. So here's some resources. I mainly use the first link. It has a lot of the equations, and it explains the Kalman filter really well. For the bottom one, you can see the code for FTC if you want to see how you code it yourself. And the middle one is the library I used for autonomous myself. So it's a really good resource. It's better than 0.5, and it's really easy to tune and build your own autonomous with it. So yeah, if y'all have any questions, feel free. And if you want to ask questions later, you can go to the website area52ftc.org. Thank you.
Okay, does anyone have any questions for Arthur? No questions? All right, thank you so much.
All right, thank you.
One question?
Oh, yeah.
How like are all filters like computationally? Are they really expensive? Or
global shutters?
no, computationally expensive for the Kalman filter?
Arthur, can you repeat the question?
Like loop times wise.
Yeah, so for loop times, for Kalman filters, loop times wise, it depends on what sensors you use. So let's say in my example, I use April tag localizer. That can add to your Kalman filter, especially when you constantly pull the detections. But other than that, if you see, oh shoot. Like if you see these are just math equations, so they don't add any extra time to your loops. So yeah. Yeah.
All right, any other questions? All right, let's hear it for Arthur.
There is a question from online folks. Please check the chat.
Oh, you have more questions in the chat.
All right. So does this algorithm take input from any sensors such as distance sensor? So yeah, you could also use distance sensors. I just, for my preference, since I did April tags last year, I just did April tags. But if you use distance sensors, you can just use that with odometry as well. But the thing with distance sensors is that it's very noisy. You just gotta tune the variance for it. So yeah. And then, how do I calculate during pathing? So to calculate the position during pathing, you can just change the update pose estimate function in Roadrunner and just apply it to that. And yeah, just change that function. Yeah.
How do you compensate for the delay in input lag measurements?
I just pretty much just added it in. I just didn't compensate for it at the time, but that's for future. So yeah. But I think yeah.
I think you have one more question at the very bottom.
No, it's just the second part of
the
question. Yeah.
All right, thank you.
I think.